Hello and welcome to the fifth and final video of the M2 chapter Variable Acceleration. Vectors-based exam question on the screen. If you've got time, pause the video, give this a go. A particle P of mass 0.4 kilograms is moving under the action of a single force F newtons. At time t seconds, the velocity of P v is given by this. I hope straight away you have in your mind the formula F equals ma, which connects our force F with the acceleration a, acceleration being something we're much more likely to be able to find from the velocity. Of course, these are both vectors. When t equals 0, P is at the point with position vector this. That sounds suspiciously like a boundary condition. When t equals 4, P is at the point S. Part A, calculate the magnitude of F when t equals 4. Okay, as I said up here, to do that we're really focused on A initially, and then we'll just use the mass to change A into F with this formula here. To find the acceleration, I need to differentiate the velocity. So for part A, acceleration is equal to the derivative of the velocity, which is 6I plus 2t plus 3j. When t is equal to 4, we put that in. A is equal to 6I plus 11j. Now we know A, we can find F. F is equal to the mass, 0.4, times A, which is 6I plus 11j, which gives us 2.4I plus 4.4j, and if it was a vector we would leave it there, but it wants the magnitude of F. So we now need to find the magnitude of F by using Pythagoras. So 2.4 squared plus 4.4 squared square rooted, and if I put that all on my calculator, it gives me 2 square root 157 over 5, or in decimal form, 5.01 newtons to 3 significant figures. Part B asks us to calculate the distance OS. Immediately two elements to this. We're going to need the distance. We don't have a formula for the displacement yet. We'll have to get that by integrating the velocity. And then OS, we're assuming O is the origin. It's not entirely clear about that, but we're assuming O is the origin, and we know S is when t equals 4. So to start us off here, we're going to find the position vector by integrating the velocity vector, and that gives us 3t squared plus 4t plus pi plus t cubed over 3 plus 3t squared over 2 plus qj. Now we need our boundary condition. When t is equal to 0, the position vector is this. Minus 3i plus 4j on the left, and on the right hand side we have 0 plus 0 plus p, so that's just pi, plus 0 plus 0 plus q, so that's just qj. So p is equal to minus 3, q is equal to 4, and our final position vector is 3t squared plus 4t minus 3i plus t cubed over 3 plus 3t squared over 2 plus 4j. But that's not what the question wants. The question wants the distance from O to S. Assuming this is the position vector from the fixed point O, then we need to know the position vector at S, which is when t is equal to 4. So if we put that into our equation, at t equals 4, we get point S with position vector 3 times 4 squared plus 4 times 4 minus 3 gives us 61i plus 4 cubed over 3 plus 3 4 squared over 2 plus 4 is 148 over 3 for the j, just by putting t equals 4 into this equation here. Finally, we want the distance, whereas this is still a displacement. So to find the distance, we need the magnitude of this, which is just 61 squared plus 148 over 3 squared, square rooted. And that gives the answer 78.4523 dot dot dot, which I will round straight away to 3 significant figures, 78.5 meters to 3 significant figures. And that is OS. In this video, we're going to apply what we've learned so far to derive the constant acceleration formulae. We can apply the ideas learned about using calculus on functions of time to derive the constant acceleration formula, sometimes called the kinematic formula. Although we're using ideas from variable acceleration, it's very important that you keep in mind that these formulas are only valid for constant acceleration. That's an absolutely key element of how we're going to derive them, and it's only going to be valid in this context. Our starting point is going to be a very general, generic starting point. So if we consider a particle moving in a straight line with constant acceleration, a, initial velocity u, and initial displacement 0 meters, then we can use integration to find its velocity v, and then its displacement s at time t. So you can see very general. The only thing we've assumed in terms of a number is that the displacement is 0. And that's very reasonable because when you start, the distance from your starting point will always be 0. So we're applying specifically the idea about integrating acceleration to get velocity. So if the acceleration is simply a constant a, not a function, just a, then the velocity is equal to the integral of a dt. And I hope at this point you can understand why it's important that this will only work with constant acceleration. Because if a is a function of time and not constant, then we need to know what it is in order to integrate that function. The only way we can do this very generally without knowing what a is if we know at the very least it's a constant, because you know we don't need to know the value of a constant in order to integrate it. So given that a is a constant, we can integrate this to give at plus a constant of integration c. Now we can use the boundary conditions that the initial velocity is u. And remember, this word initial just means t equals 0. So when t equals 0, v, the velocity, is equal to u. Putting that in here, then we get u is equal to a times 0 plus c, which gives our constant as u. Putting that back into our formula for velocity gives us the final answer of v equals at plus u. And you might be a bit more familiar with u plus at. Here is our first constant acceleration formula, derived directly by integrating a constant acceleration. To get our next constant acceleration formula, we simply take this one and integrate it again, because we know integrating the velocity function will give us displacement. And this is a function of time, but we know what the function is. It's a linear function if the acceleration was constant. It's at plus u. Integrating this gives us at squared over 2 plus ut plus another constant, I'll call this one k. And now we can use the boundary conditions that we have initial displacement 0 meters. Again, initial means t equals 0. And when t equals 0, obviously the displacement from its starting point is 0 because we haven't gone anywhere yet. Putting that in gives 0 equals a times 0 over 2 plus u times 0 plus k gives k equal to 0. So our formula is s is equal to 8t squared over 2 plus ut, and again you might be more familiar with it written the other way around, ut plus a half at squared, our second constant acceleration formula. From here, to get the other three formulae, we simply rearrange this and substitute it into here in order to get rid of the different variables. If we rearrange v equals u plus at to give u equals v minus at, we can substitute that now into the s equals ut plus a half at squared formula to eliminate the variable u. And that will give us v minus at times t plus a half at squared. And if you expand that bracket, you get vt minus at squared plus a half at squared is minus a half at squared, which is our third constant acceleration formula. Rearranging this in a different way to give a is equal to v minus u over t, and substituting that into this formula down here gives s is equal to ut plus a half times v minus u over t times t squared. One of the t's cancel out, giving us ut plus a half vt minus a half ut. Ut minus a half ut gives us a half ut. So we have a half vt plus a half ut, and factorizing that gives us a half t u plus v, which is our fourth constant acceleration formula. Finally, if we rearrange it instead to make t is equal to v minus u over a, therefore t squared, v squared minus 2uv plus u squared all over a squared, and substitute it into here, we get s is equal to u times t, so that's uv minus u squared over a, plus a half times a times t squared, so a half times a times this expression, and the a will cancel with one of the a's on the bottom, and the half will put a 2 there as well. So we get a v squared minus 2uv plus u squared is all over 2a. Now if we multiply everything by 2a to get rid of this fraction, we get a 2 coming up here, and a 2a over here. 2as is equal to 2uv minus 2u squared plus v squared minus 2uv plus u squared. You can see that this term cancels with this term. This one cancels one of these to make v squared minus u squared. We bring the u squared on the other side, and we get the final expression squeezed in the corner here. V squared is equal to u squared plus 2as, our fifth and final constant acceleration formula. Sorry, this one was squeezed in here a little bit to try and get them all onto one screen. So that's all 5 formulas derived from the very simple starting point of the acceleration being constant means you can integrate it to find the velocity, integrate it again to find the displacement, and then combine those formulas in different ways. The constant acceleration formulas, as I'm sure you know, are very, very useful, but I hope this has shown that if you didn't have the formulas, or if you were asked not to use the formulas, you can still do questions like this from a variable acceleration point of view, just with the acceleration function as a constant. That, I hope, is enough for you to have a go at some of the questions from exercise 2F, and that's the end of the chapter, so you can also do the chapter 2 review exercise. Maybe I'll see you for chapter 3.